In this video, we are going to be discussing one of the types of magnetism exerted by materials. Now, there are three types of magnetism. There is diamagnetism, paramagnetism, and ferromagnetism. And what distinguishes each of these types is the processes that occur within the atoms or the molecules that comprise the magnetic material. Now, I've already talked about paramagnetism and ferromagnetism, and we analysed that through the lens of statistical physics. But in this electromagnetism course, we are actually going to be discussing diamagnetism, and we're going to be revisiting paramagnetism, but this time we won't be applying statistical physics, we'll be applying a more classical derivation. However, with ferromagnetism, you do essentially need to use statistical physics and the Ginzburg-Landau theory of phase transitions, which I've already done a video of. So in this video, we're going to be discussing diamagnetism, and we're going to be discussing the processes that occur within the atoms that cause materials to become what's known as diamagnetic. So, without further ado, let's get into it. Now, diamagnetism is present in very specific types of atoms, and it's that specificity which is actually what causes these types of atoms to become diamagnetic. And the types of atoms in which it is present are atoms which have a full shell of outer electrons. So this would include elements like helium or neon or anything which has a full shell of outer electrons. So this would be something like neon, which has 8 electrons in its outer shell, and then it would have 2 electrons in its inner shell. Or you could go with helium, which has just, of course, 2 electrons in its outer shell. And the reason why these atoms have to have a full outer shell is because atoms which have a full outer shell actually have 0 angular momentum. So in quantum mechanical terms, the angular momentum of the atom actually sums to 0. And the consequences of this are that because the angular momentum is 0, if there is no magnetic field, then the magnetic dipole moment is also 0. Let's go back to our kind of picture of just a single electron that's orbiting a nucleus right here. So there's our electron, and it's orbiting around a nucleus. And this from the last video is what we said induced the magnetic dipole moment to occur, because of course you have an electron that is orbiting around a nucleus, and whenever you have a orbiting electron, then that basically means that you have a magnetic dipole moment, M, right here. So how do we calculate what the magnetic dipole moment is for this situation? Well, we said that M is simply equal to the current times the surface area, which it's sweeping out. And of course, if we say that this distance right here is just r, the radius of the orbit of the electron, then we can say that S is simply equal to pi r squared. Because of course the area of a circle is pi r squared. So that bit's easy. And if we take the upwards direction to be the z-axis, then we can say that this is in the z-hat direction and it's pointing upwards right there. So that was the easy bit, but what about the current? Well, the current, we know, is the rate of change of charge, or the amount of charge passing a point per second. But what is delta t? Delta t, that's just the time change. It's just the distance over the velocity. So if you just divide distance divided by speed, if you have a constant speed, which is what we have right here, then we can simply get what delta t is. So what can we put in this? Well, if we take one period of this orbit right here, then we say that the distance is going to be 2 pi times the radius, because of course the circumference of a circle is 2 pi r, just divided by the velocity, v, right there. But we can actually express this in terms of the angular frequency, omega, because of course v is equal to omega r for any circulating orbit. And we can just simply express this as 2 pi divided by omega. And this, of course, would apply to anything which is orbiting in a circle, but just to go over it once more, just for convenience. So that's delta t, but what about delta q? Well, delta Q is just simply equal to the charge of an electron. That's just minus E right here. So if we substitute both of these into this equation for the current right here, then we're just simply going to get minus E omega divided by 2 pi right there. And so now that we have the current, we can then go ahead and calculate the magnetic dipole moment, which is of course going to be the current, which is minus E omega over 2 pi, multiplied by the area, which of course is, we said, was pi r squared. And this magnetic dipole moment is going to be in the z hat direction right there, so pointing vertically upwards in this case. So the pi's are going to cancel, and we're just simply going to end up with minus E omega r squared divided by 2, z hat direction. But what is the definition of angular momentum in the classical sense, L right here? Well, as a scalar, we know that the value for the angular momentum of any orbiting body is simply equal to the linear momentum multiplied by the radius right there. So this will just be the scalar, this will just be one component of the angular momentum right there, but of course it would be a vector normally. And this is just, of course, mvr, because of course momentum is just mv. But of course we said that v is omega times r, so therefore we can write this as m omega r squared. So let's go ahead and compare this expression to this expression right here. What is that going to be? Well, we have an omega r squared right here. And so if we rearrange this equation for omega r squared, we're going to get that omega r squared is simply equal to L divided by m right here. So we can say that the magnetic dipole moment right here is simply equal to minus E over 2 times L divided by m right here. And of course, angular momentum is a vector, and in this case they will both be pointing in the z direction right there. And of course, if both are pointing in the z direction, then we can say that L as a vector is equal to L z hat. So therefore we can just vectorize this angular momentum right here. And this ratio right here, this minus E over 2m, is known as the gyromagnetic ratio and is often given the symbol gamma. And this is equal to, in this case, E minus E divided by 2m. So you often hear the relationship between the magnetic dipole moment and the angular momentum just written as the gyromagnetic ratio. The interesting thing comes when we apply a magnetic field to our orbiting electron. So we have our system right here. We have our nucleus and we have our electron that's orbiting right here. And of course we know that it's producing a magnetic dipole moment. Now normally for a static current, the torque tends to line up the magnetic moment with the magnetic field right here. But what happens in the case of an orbiting electron? Well, in the last video we said that the torque is equal to the magnetic dipole moment cross-producted with the magnetic field. But of course torque is just the rate of change of angular momentum. But of course we said just now that this m is intrinsically linked to this angular momentum right here. So we have a situation where if we apply this magnetic field, we get a torque, but this torque will produce a change in angular momentum that is perpendicular to the angular momentum that is already there. And this gives rise to something really quite interesting and also very complicated. So if we have a change in angular momentum that is perpendicular to the angular momentum that was already there, this gives rise to a phenomenon that is known as precession. And precession is basically where you have a situation in which the axis of rotation is actually spinning right here. So rather than just having a spinning object, you actually find that the axis of rotation is actually sort of wobbling like this. And it's that precession, it's that kind of orbiting axis of rotation of the atom, which actually gives rise to diamagnetism, because of course when we have something that's orbiting, if you have something that's like a charge that's kind of doing some kind of orbital motion, that induces a magnetic dipole, therefore goes on to induce a magnetization, giving rise to diamagnetism. So let's go ahead and see if we can calculate what the precession frequency and thereafter the diamagnetic susceptibility is from what we've just described is going on. So I'm going to redraw this vector diagram in order to make sure that we understand kind of what directions everything is in whilst we're calculating. So we have our magnetic dipole moment right here, which we could also write as the angular momentum. So we could write this as M or L. This is just the magnetic dipole moment caused by the electron orbiting the atom right here. This is what we said before. But of course, we now apply this magnetic field right here at an angle theta. So this is B right here, and this is either M or L. And we said that this would give rise to a change in angular momentum that is perpendicular to both the magnetic dipole moment and the magnetic field, because of course the torque is M cross B, and the cross product produces a vector that is perpendicular to both. But of course, because the magnetic dipole moment is proportional to the angular momentum itself, the change in angular momentum right here, delta L, will actually be along this kind of circle right here. So let's go ahead and write out what the torque is in terms of the angular momentum. So we said that torque is delta L divided by delta T right here. Well, the angular momentum in the same direction as B is of course L sine theta. So for delta L, we can write L sine theta. But of course, there's going to be another angle that we're going to have to take into account, and that's the angle of precession right here. This is the angle between the B vector and how much the angular momentum vector is sweeping out whilst it's orbiting. So of course, it's orbiting right here, and this angle right here, which we're just going to call phi right here. And so in time delta t, it will just sweep out angle delta phi right there. And this will be divided by delta t. And of course, we said that the torque was equal to mb times the sine of theta. And we're just going to keep this as a scalar equation for now right here. But of course, we said that L is equal to 2 times the mass of the electron divided by the charge times the magnetic dipole moment. And yes, I'm aware this is very confusing because of course we have this m being the magnetic dipole moment and this m being the mass. And so what I'm going to do is I'm essentially just going to put m subscript e, which you'll often see it being denoted as the mass of an electron. So that right there is the mass of an electron, and this right here is just the magnetic dipole moment. So substituting in, we're going to get 2me divided by e times the magnetic dipole moment times sine theta delta phi divided by delta t is equal to mb times sine theta. Sine thetas are going to cancel out, as you can see right here, and we're also going to have a magnetic dipole moment factor cancelling out right there. And so if we rearrange this for b right here, we get that b is equal to 2me times m divided by e times delta phi divided by delta t right here. And I'm going to define delta phi times delta t as the precession frequency right here, omega p. So this is the frequency at which the atom is precessing on its orbit and the time taken for it to get back to its original precession angle right here. And so we get that the precession angle is equal to EB over 2m, or since E divided by 2m is sometimes known as the gyromagnetic ratio, we can also write this as equal to minus gamma times B right there. So this is the precession frequency, and this is the frequency at which the axis takes to complete one full cycle. But of course, we said that this precession generates an additional magnetic moment. So let's go ahead and just draw out what we have. So we have our atom orbit right here with our magnetic dipole moment, and it has a magnetic field. But of course, this magnetic field is sweeping out an additional orbit, essentially, which is producing another magnetic dipole moment, because of course we have this changing orientation. So how do we calculate this additional magnetic dipole moment? Well, let's call this delta M. So this, just as a scalar for now, is equal to the implied current, because of course it's not an actual current this time, times the surface area. For S, we can simply substitute in pi r squared, where r was the radius of our atom. But for the implied current, this time we're going to get E divided by 2 pi times omega precession, which is our precession frequency right here. And that's going to be multiplied by pi r squared, the area right there. But of course, we said that the precession frequency is equal to EB divided by 2m right there. So substituting that in, we get E divided by 2 pi times the precession frequency, EB divided by 2m, E right here, I should just write the subscript E, otherwise we'll get very, very confused, multiplied by pi r squared. And so these E's are going to double up. We're going to get an E squared, R squared, divided by 4m times B, because of course the pi's are going to cancel out right here. And so this right here is the actual magnetic moment that is produced, which actually causes the macroscopic effect of diamagnetism, because of course we said before that the magnetic moment caused by the electron doesn't actually contribute anything to the diamagnetism. It's this right here that actually is the magnetic moment that fundamentally causes diamagnetism to occur right here. So we have our formula right here for a single electron that is orbiting a nucleus, having a magnetic dipole moment to begin with, but of course the precession of that orbit inducing this actual magnetic dipole moment, which contributes to the overall effect of diamagnetism. But of course, there's quite a few things we need to consider, because this is just for one single electron in one single atom. And of course, there's going to be Z electrons per atom, because of course there are Z protons in an atom, and so therefore if it's not an ion, then you're going to get the same number of protons as electrons, and therefore you're going to have Z electrons per atom. The other thing is that of course the magnetic dipole moments won't all be pointing in the same direction across each atom. Some might be more in the direction of the field, whilst others might be completely off the direction of the field right there. So they could be across all values of theta. And one of the things we're going to do is we're actually going to try and average out across the entire domain of theta, that is between 0 and pi radians, to try and figure out what the average direction is that these orbits are going to be with respect to the magnetic field. And the other thing is that of course, we've just been considering a loop of current, whereas of course, in reality, it's going to be more like the nucleus at the center of some kind of sphere of cloud charge right here. So instead of it necessarily orbiting like that in a loop of current, we're going to have it sort of orbiting around in a spherical geometry right there. So you can have different electrons all orbiting around kind of a little bit like that. So there's a few different things to take into consideration. So what we're going to have a look at is we are going to take the average magnetization across the entire solid. And so for that, we are just going to put this in angle brackets and say that the average magnetization across the entire solid is going to be, well, the charge is going to be the same in each case, E squared, and so is the mass of the electron right here. That's going to be the exact same in each case. And of course, B isn't going to change either. But of course, the R squared value is of course going to be different. And we also said that there was going to be Z electrons per atom. And so we need to take an average of this kind of R squared value, the mean squared distance between the electron and the atom. And how are we going to calculate that? Well, we need to essentially average over the entire range of theta, where theta is the angle between the magnetic field and the dipole moment. And so if we say, for convenience, that the magnetic field is simply in the z direction, then if we go back to our diagram right here, then it's only going to be the z component of the magnetic dipole moment right here that is actually going to contribute, because of course we're taking the z component to be upwards, it's only going to be the z component that is going to contribute to the overall effect, if you like. Because of course, if it's orbiting around the z-axis, then we essentially need to average out what the orbit is going to be between sort of the center and the very edge right here. And so therefore we need to multiply this r by cos theta right there. And so we get that the average dipole moment is going to be z e squared b divided by 4me times r squared times cos squared theta right here, because of course each r needs to be multiplied by cos theta, so therefore r squared will therefore become r squared cos squared theta. We need to average this across the entire value of theta, which is of course between 0 and pi radians. So let's just go ahead and rewrite this prefactor right here. And for this term right here, this is going to be an integral of r squared cos squared theta. And because of course we're in spherical geometry, we have to multiply by a factor of sine theta when doing the integration, because of course the spherical element is of course sine theta d theta. And this is going to be over the range of 0 to pi right there. Now, this r squared is of course a constant in terms of theta, so we can actually move this outside the front right here. And we have this integral of cos squared theta times sine theta over theta between 0 and pi. Now, this is actually quite a common integral, so it might be worth actually going through and learning how you do the integral, but once you kind of remember the result, it might be worth just sort of holding on to that result. So we're going to get ze squared br squared divided by 4me. And how are we going to tackle this? If we do our usual u substitution, we let u equals cos theta. Then if we take a derivative, du by d theta, we get that this is equal to minus sine theta. And so rearranging this, we get that minus du is equal to sine theta times d theta right there. So let's go ahead and transform this integral in terms of u. So the limits are going to change, and if we get at theta equals 0, we get that u is equal to 1, so therefore we write the lower limit as 1, and when theta is equal to pi, we know that u is equal to minus 1, so we get this is minus 1 right there. This is just going to be u squared, and we're going to get a minus du right here. So this is just going to be a fairly straightforward integral of u squared times du. And what we can actually do is we can take this minus sign away, but we can also reverse these two limits right here. So rather than it being between 1 to minus 1, we can say it's between minus 1 to 1. And the trade-off for doing that is we get rid of this du right here. And so when we integrate this, we are going to get 1/3 of u cubed between minus 1 and 1 right here. And if we simply substitute in these limits, we get that this is going to be 1 cubed minus minus 1 cubed right here. So 1 cubed is just 1 minus minus 1 cubed. That's just going to be minus minus 1, so that's going to give 2 right there. So this can all become 2 right there. And so we get that the factor in which we have to multiply by is just simply 2 divided by 3, so just 2/3. So we're going to get 2/3 times this original value right here. And this is actually quite a common thing, is if you have to take an average of something over the sphere, you often see this 2/3 factor. And this is something that might come up in a couple of other occasions in physics. So this is our average magnetic dipole moment. across the entire system of atoms that we are considering right here. And so what we can say is that the magnetization is simply equal to the number of atoms per unit volume multiplied by this average magnetization right here, because of course we've averaged it out, and so we therefore can just simply multiply this by the number of atoms per unit volume, and then we will have the macroscopic magnetization. And so this is equal to 2/3 of this just gives this a factor of 6 rather than 4. So this is just going to be ZE squared times BR squared divided by 6ME times this N right here. And what we can actually say is that for weak magnetic fields, because of course diamagnetism is a fairly weak effect, we can actually say that B is equal to mu naught times H right here. So the external magnetic field is kind of the same as the magnetic intensity right here. So B is equal to mu naught H, and therefore you can simply substitute mu naught H into this equation right here. And now we can finally write what our diamagnetic susceptibility is. We get that this is equal to M divided by H, because of course that's what the diamagnetic susceptibility is. And so we can say that this is mu naught ZE squared R squared times N right here divided by 6ME right here. So there we go. This is a general formula for the diamagnetic susceptibility right here. And what you actually find is that in the idealistic scenario, so for perfect diamagnetism, you actually get that this tends towards -1, and that is the maximum amount of diamagnetic susceptibility you can possibly get. But this is the general formula for it, and as I mentioned before, it is a fairly weak effect, and it actually turns out that all materials are technically diamagnetic. The reason why materials with full outer shells are said to be dielectric is because that is the dominant form of magnetism within those types of materials. And in the majority of other cases, the other two types of magnetism, such as paramagnetism and ferromagnetism, are far more dominant. So there we go. I hope that was really, really useful. And in the next video, we're going to be looking at paramagnetism. And we're going to be deriving a similar formula for the magnetic susceptibility in the case of paramagnetic materials. So I really hope that was useful, and I will see you guys in the next video. Take care.